There are very few queuing theory jokes. On the other hand, it's been found extremely useful for analyzing computer systems, computer networks, and other technology systems. So we're going to spend time doing that. Let's get a little bit of the overhead out of the way. My office is just down the hall this way at 3732G, but also this room itself, which is 3440 Belter Hall. And my office hours are the hours immediately following this class. So it's Monday and Wednesday from 4 to 5. If you need extra time, you can try to reach me with email, etc. Now, I want to tell you immediately, we're going to have to change one class meeting. There'll be no class on March 6th. There's going to be a makeup class for that at a time when nobody in this room probably has another class. And guess when that would be? Friday from 2 to 4. Now, I may be mistaken, but I hope all of you can make that. So the makeup class is going to be on Friday, Feb 16. It's not Valentine's Day or anything like that. From 2 to 3:50. Now, the grading is going to be based on 3 quantities: your homework, midterm, and a final. And the homework will be graded least of all. It's going to account for 5% of your grade. And the homeworks, which we want you to hand in, will not be graded. If you hand it in, you get the credit for the homework. Don't send me Shakespeare. Send me something about the problems we asked you to solve. And so let's mark that down. The homework is 5%. The midterm is going to be 40%. And the final, if you can do the subtraction, is 55%. Now, the homework itself is going to be handed out. It's going to be assigned typically on a Wednesday, say, of week N. It'll be due basically on Wednesday of week N plus 1. And the solutions, which we posted, will be available typically on Friday of week N plus 1. Your first assignment is already on Bruin Learn. Look for it on Grade Scope as opposed to Bruin Learn. It's easier to find it there. And you'll hand the assignments in there as well. So it's released on Gradescope on Bruin Learn. Now let's talk about the exams. They're going to be closed book. No little papers, no little notes on your fingers, no cheats on the wall. Closed book. And I understand that you may be concerned that if you forget the magic formula for Part A, then you can't do Part B, C, D, E. And that will give you a certain amount of concern. Don't worry. You can buy any answer during the exam. If Part A is worth 3%, you want it, I'll give it to you, minus 3%. So don't worry that a critical bit of information is forgotten. You can get it. Just come up, I'll be here, and you buy it. With points, not with money, not with Bitcoin, with points. Okay. So the textbook. You should all have seen that the textbook is the following. It's queuing systems. And by the way, see the word queuing is spelled? This extra E here, that E is magic. The British spell it this way. The Americans typically spell it without that E, but with the E, you have 5 vowels in a row. There's no other word in English with 5 vowels in a row, except if you want to stretch it, the word meowing. You know, cats go meow, but that's not really right. I mean, people can spell that any way they want. So I like to spell it with the 5 vowels. So it's queuing theory, queuing systems. Sorry about that. Volume 1, theory. And here's what the book looks like. And where do you get it? It's a book written by me. You can get it at www.alibris.com. Or www.abook.com. Or on Amazon. But more importantly, at the break, one of your classmates is going to tell you exactly how to get it. Okay, so just listen at the break. And my lectures are almost, but not quite, verbatim from the book. Therefore, you don't have to take down everything I write or every equation I put down. Take notes and say, this looks important, I'm confused about this. But don't try to copy everything, because it's all in the book. And you'll spend your time writing instead of thinking, and I want you to think. Because this course is about giving you the ability to solve problems for which queuing theory is a correct tool, to formulate them, to find mechanisms for solving them, etc. It's an engineering approach as opposed to a pure mathematics approach. We're not going to study measure theory. We're not going to go deeply into stochastic processes. But we're going to go deep occasionally to show you it really does work. But I want you to extract out of that the fact that you understand what's going on, you see the tools, you know how to use them, and you feel comfortable to apply them and make your own models and solve problems. That's the whole purpose here. Now, it turns out in the textbook, there is an errata sheet. And I've already sent it to you, and here's what it looks like. You've already got that on the gradebook, on the modules, and there are quite a few errata worth looking at. They're not critical, but they're important. Now, the errata sheet, of course, is not in the book. It's in something called a solutions manual, which you can find if you like, and this is the solution to all the problems that are assigned from the book. But I want you to solve the problems yourself. You're the ones who are getting educated, not me, okay? You know, the answers are here, but try to solve them. If you run into trouble, then look it up. You don't have to get this. It's available. I don't necessarily recommend you do that, because I'm going to give you all the solutions the Friday after the Wednesday exams are due, the homeworks are due. Okay. So let's return now. Okay, now I've already assigned you probably didn't see it, you should be reading Appendix 1 and 2. It's in the back of the book. So I want to remind you that. Because that's going to be the first few lectures. So any questions about the administrative issues here? Be sure to hand in your homework. Oh, by the way, the exams I grade pretty tough. But the final grade for the course, I'm relatively easy on. So I want you to see where you make mistakes on the exams, so you'll learn from that. And some of the problems can be pretty hard, even the homework problems. They're meant to give you additional understanding as to what's going on here. Okay, so let's get at it. Let's talk about queuing theory. So a queuing system is a system some kind of a system to which you arrive, you hang around a while, and you leave. Right now, you're in a queuing system. You came into the class, you're going to hang around a while, and you're going to leave afterwards. Life is a queuing system. You arrive, hang around a while, and you hope to maximize your time in that queuing system, then you leave. So in fact, so many things can be modeled as a queuing system, or it's basically a system of flow. And in the system of flow, things arrive, they stick around a while, and they leave. So let's talk a bit about that. Okay, let's talk about the arrival rate. Whatever it is, it's, say, at a rate R, things per second, customers per second, messages per second, gallons of water per second, whatever. And there's a service rate, or a capacity, which we denote by C. Again, same units. And in order for the system to be sustainable, R should be less than C. If you're trying to throw in more things that the system can get rid of, it's going to explode. Now there's one exception. The rate can equal the capacity if everything is deterministic. Every 1 second something comes in, every 1 second something leaves. Then the rates can be the same, but that's the only case. So in general, you want things to arrive slower than you can deal with them. Okay? Now, in the case of deterministic systems, I just gave you the answer. It's a trivial system. There's nothing to solve. The more interesting thing is if there are unpredictable arrival times and unpredictable service times. Then you got to wonder what's going on in the system. How many things are there? How long do you spend in the system, etc. We're going to solve for that. That's going to be the things we try to get. But in general, not only for what we call a queuing system, but any system of flow, the following is true. That the rate of increase in the system is equal to the rate in minus the rate out. And that's a time-dependent function. The rate of increase, the rate of flow can change over time, and so can the flow out. But in general, this is a time-dependent equation. Now, if in fact there's a steady state, then the rate of increase will be 0, and it'll just say that rate in equals rate out. Now this apparently simple equation is very powerful. You're going to use it to solve some very sophisticated queuing problems. And just say something can't accumulate, so whatever's coming in has to come out at the same rate. And you may not understand what I'm saying right now, but understand that that simple concept is going to run throughout what we do. Now, as I say, steady flow is a trivial system. But if you have this steady flow, which means deterministic, you know exactly when things are coming in, how big they are, how long they spend. If you have them go through a sequence of channels, say, a railroad network across the United States, or an automobile network, or a freight network across the world, then you have issues other than worrying about the unpredictability. You like to know how much. Suppose I gave you a complicated road network for this country. You know how many cars per second can flow on a given length of highway. And I asked you, what's the maximum rate you can move from Los Angeles to New York? What's the maximum rate in this complicated network I'm going to draw? So here's such a network, okay? Suppose these are directed network lines. And I tell you, this link can carry, say, 10 units of whatever. This can carry 5, this can carry 2, etc. How much you can get from LA to New York? Well, the theory behind solving such problems is called network flow theory, and we're not going to touch it. But it's a very interesting field. Maybe you've heard of something called the max flow min cut theorem. If you haven't, you should look it up. It's a great theorem. And it tells you the maximum flow you can get by looking at a network like this, using some rather straightforward calculations. But we're not going to touch that. Instead, we're going to study this system when things arrive at unpredictable times and things spend unpredictable amounts of time getting served in there. Now, if you have a network like this, where each of the links basically is a system where the arrivals are unpredictable and the service rates are unpredictable, a good example, the internet. You have messages flowing in. Some of them are longer than others. They take different paths. They converge. Flows merge. How do you solve what's going on in a network like that? Well, you have all the problems of queuing theory, which are hard, and all the problems of network flow theory, which are hard, and you end up having to do some approximations. But that's the big picture. We're going to focus very closely down on this system, where things arrive to a single system. There may be more than one server here, but you only have one thing to do when you're in there individually, and you come out. Okay. So let me focus again. We're going to study on unsteady flow. And in particular, the arrival times are unpredictable. And the service times, how long you, an arriving customer, needs to be served by whoever's serving you in that system. The amount of service you need, the service times, are also unpredictable. And we're going to look at a single channel, unsteady flow, through a single channel, not a network. That's called queuing theory. Now, what do you want to find? If I described statistically the arrivals and the services, that's the input of the system. Now, what do you want to solve about the system? Things like, how long do you spend in the queue? I'll call it the waiting time in the queue. Or the total time spent in the system. Or how many people are in the system? In computer science, we talk about the size of the buffer. How large a buffer do you need to hold these people that are sticking around, if they're messages, for example? You'd also like to know fraction of time the server is busy. And that better be less than 100%, or otherwise it can't handle it. Well, is it 2%? Oops, inefficient. Is it 99%? Getting a little touchy here. So you like to be able to calculate that number. How big is it? And there's other issues. For example, how long does the system remain busy until it goes idle again? How long does it remain idle until it goes busy again? What if the server breaks down? What if customers join the queue and then leave before they get served? That's called defection. Or what if an arrival looks at the system and says, oh my God, I won't join? That's basically balking. What if there's a cost to start up the server, etc.? What if the server decides to go on vacation? All these are models that have been solved in the queuing theory literature. And they all occur in practice, yes? The system is the box. This room is the system. I'm the server right now, and I'm serving you as a group service, a bulk service right now. You're all getting served simultaneously. But the arrivals come in. Now, if I was a bakery store clerk and you all wanted to buy a bagel, I'd serve you one at a time. There'd be a queue, some kind of a queue. Maybe it's disorganized or organized. I serve you one at a time. The amount of time I need to spend with you is the service time. And it's typically unpredictable. Each of you may have a different amount of service. Yes, go ahead. The queue is part of the system, which was your question. The other issue you basically raised by saying that is, in what order should I serve people? First come, first serve is natural, and most of the time we assume it's first come, first serve. But it could be last come, first serve. It could be biggest person, smallest person, richest person, interesting clothing, the bribe I get, you pay for your position in queue. It's classes. This group gets priority over this group because for whatever reason. So all those issues have been solved and modeled and solved in queuing theory. So it's a rather rich area, but you have to think about using it in the applications you have in mind. Do you want to model, for example, the way a time-sharing computer system works? Well, you can do that. Okay, the jobs coming in are the arrivals. The time that the processor spends on it is the service time. And it's a highly preemptive service system in time sharing. You get a little bit of your job done, then he gets some, then you come back again and get a little more. So there's rather interesting situations. You're basically opening up the richness of this field. But the simplest one is a single queue, a single server, first come, first serve, and some statistics on when people come in and how long they spend in the service when they get to the server. That's the simplest model that we'll be looking at. Okay. Now, in order to attack the system, you need some tools from before you came into this class. And I'm going to go over them with you. Basically, it's appendices 1 and 2. What I want to do is I want to start by talking about basically transform theory. That's appendix 1. And the other one we'll get to next session is a probability theory refresher. Hopefully you've all been exposed to probability at one point or another. I'm going to take you through the basics. You can get along if you haven't had probability theory, but it sure helps if you have. And the appendices go over this in a fair amount of detail. Okay. So let's talk about transforms. Now, why do we study transforms? And why do exponential functions, why do they happen to appear in so much of what we call transform theory? Well, the reason we want to study transforms is because they help us solve linear time-invariant systems. And I'll define what that is in a moment. You should know, but I'll define it anyway. And those systems lead to basically either differential equations or difference equations, which transforms help us solve. But those of you who had any exposure to Fourier series, Fourier transform, Laplace transform, Z transforms, you may have seen the notion of exponentials popping up in them. And the first question you should ask is, where did they come from? Did some brilliant mathematician say, exponentials, I'm going to invent them, and here they are? Or nature give them to us? And what do you think the answer is? Anybody? Guess? Two answers. One, a mathematician or nature? Yes. Good, you're right, nature. It was given, nobody had to discover them. They came out automatically. And you're going to see why in a minute. Okay. So basically, they arise in what I call linear, time invariant systems. And I'm going to abbreviate that as LTI when I talk about it. So let's look at some kind of a system now. And I'm going to say that is a system with some properties. And the one I want to think about is one in which I feed in some signal, some function of time into this system. And it does something to that signal, and out it delivers some other function of time, g of t. Now that's not quite describing a queuing system, but I'm trying to describe the basis for which transforms arise. So the notation for what I just drew in shorthand will be f of t gives rise to g of t. And it's a single bar, single line, single arrowhead, because I'm going to use some double notation later. So that simply means you pump in a signal f and you get out a signal g. Now, if f1 of t, a particular f1, gives rise to a particular g, called a g1 of t, and if f2 of t gives out something else called g2 of t, then the system is linear if, when I put it a little bit of f1, say an amount a of f1, plus some different amount of f2, say b of f2, that input gives rise to an amount a of the first output, g1 of t, plus an amount b of the second output, g2 of t. If that's the case, then it's said to be linear. I'm sure you've seen this many times in your education before. Now, moreover, we want to define something called time invariance. Just a moment. Okay. If some function f shifted in time by tau seconds gives rise to the same thing it would have, but also shifted by tau seconds, then we say it's time invariant. So I've just defined for you what I abbreviate with the notions LTI. I'm now talking about a system which is linear, time invariant. I want both of those properties. And for these systems, complex exponentials appear automatically. And complex exponentials are basically the building blocks of transforms. They're called eigenfunctions, characteristic functions, and basically the invariance of LTIs. So we're going to see them pop up. So such eigenfunctions, I'll call them eigenfunctions for the moment, is an input, let me call it f of t for the minute, such that when I put it in, I get it out again, possibly with a multiplier. And let's call the multiplier for the moment capital H. Put it in, you get it out. Now for linear time invariant systems, there's only one function that satisfies that. And that function is e to the st, where s is a complex variable. And h itself, the amount of that guy you get out, may depend upon a parameter h of s. Depending upon a complex exponential, you'll get a different amount of it out, but you get the same function out. Okay. Now here's the question. If I know what all the h's are, then if I put in e to the st, I know what to get out. I get h of s times e to the st. If you give me an arbitrary function, and if I could write that function as the sum of exponentials with different multipliers perhaps, then I know what each of those terms will give me out. Each exponential gives itself out with a multiplier. And I know the multiplier h. We assume we know h. So take an arbitrary function. If you could write it as a sum of exponentials, and you put it through a system, you know what you're going to get out. Just add up the outputs. Remember? Basically, it's linear. What a great tool. Now, can functions be written as sums of exponentials? You've all thought about Fourier transforms to Laplace transforms, as we'll see. The answer is yes. To as close an approximation as you like. You can write an arbitrary function. So, what a great tool. I can figure out what the output g of t will be no matter what f is, because f will be a sum of exponentials, and I know what each exponential gives me. The exponential gives me that. Gives me itself times the multiplier h. So that's basically the reason these exponentials are so valuable. Okay. Now, if I continue this, this will lead me to something called Laplace transforms. But I want to simplify it a little bit. It's better to go not to continuous functions of time, but to discrete functions of time. It's a little easier to deal with that first. And that's going to lead to something similar to Laplace transforms, and then we'll go to Laplace transforms. So, let's write f of t. Let me first say, we want to go to first go to discrete time functions. So we're going to take an excursion here because it's going to appear in our queuing theory very clearly. Okay. So let's take f of t and say that f of t is only occurring basically at a multiple of capital T. So let's write that as f of t at the times some multiple n times t. So every t seconds something can happen, but not anywhere else. So I'm going to write that f sub n is f of t equals nt. So the only time instance when you can get anything is at multiples of capital T. Now also, so n is the time index, if you will. Now suppose the system is discrete also. Not only is the input discrete, assume the system is discrete, which means that when you put fn in, you get out a discrete function we're going to call gn. The output is also only occurring at multiples of capital T. And I write that as f of n gives rise to gn. Now, if it's linear, we know what that means. That means if I take a times f sub n of one function plus an amount b of f sub n of a different function, I'll get out the sum of the output they would have given me. So get a of g sub n super 1 plus b g 2. And for time invariance, get the same kind of thing, that f of n shifted by m units of time will give rise to that same output g also shifted by m units of time. And so the eigenfunctions of this discrete system are the following. It's f sub n, and I'll write a super e for eigenfunction. They are, we saw it was e to the s capital T, but it's nt, so that's e to the s nt. Those are the eigenfunctions. And by the way, what I didn't do was to prove that exponentials are the only things that pop out when you put them in. The proof is in the book. It's just a few lines. I'm not going to take the time now. It's true. So that's where nature gave it to us. It was waiting for us to come. Okay. Now I want to define this constant here. I want to define the quantity z to be e to the minus s capital T, which means that f sub n, the eigenfunction for discrete time, will be z to the minus n. And because it's an eigenfunction, z to the minus n is going to give some output related to an h. Z to the minus n will give rise to count h, which depends upon the complex variable z, times z to the minus n. You put in z to the minus n, you get it out. It's just like the exponential, but in discrete time. Now, the whole reason for going here is because it simplifies the analysis of linear time invariant systems. Now, that minus n, the minus sign seems a little odd here, and it is odd. It's useful when we're dealing with systems that I described a moment ago. But for the purposes we're going to use in queuing theory, we're going to define a slightly different function. So bear with me a minute while we do this. I'm now going to introduce the z transform. So let's consider some function, some discrete function, which we call f sub n. And that's good for n equals 0, 1, 2. I'm going to assume it only exists for positive, non-negative integers. And if you want to draw a picture of it, let's take an example. If I plot fn here, n is on this axis, so here's 0, 1, 2, 3, 4, etc. This fn takes on some values, some arbitrary values, etc. And now I want to write that function in some simple way. What I want to do, I want to tag. I want to tag each function, each fn, each value of f at time n, with the quantity z to the n. Z is a complex variable. So I'm going to take Fn, and I'm going to want to write it as Fn times Z to the n. And I'm going to literally tag it, so when I put a bunch of these guys together, I can pull the Fn's out. Whatever is multiplying Z to the n must be Fn. And here's the function I'm going to try to write down now. I'm going to define capital F of Z as the following, by definition: the sum on all values of n of Fn times Z to the n. And it's important to notice that this Z to the n is really just a tag. So if you give me a power series in Z, I can pull out Fn's. Whatever multiplies Z to the n is Fn. Just a simple way of tagging it and coloring it. Okay, just keep that in mind. It looks like a strange item, but it's not. Now, what I've done, I've mapped little fn into capital F of Z. Turns out that f of z is in fact called the Z transform. Of f sub n. And we write it this way. We say Fn maps into this function capital F of Z. And notice I've written that with a double bar, double-headed arrow, which means they are a Z transform pair. Okay? And the double arrow means you can go from Fn to F of Z from the equation above. And there's also a way to go from F of Z back to Fn, which I've yet to show you. Okay? So let's do an important example. Let's let Fn be equal to A times alpha to the n for n equals 0, 1, 2, etc. Now, I'm going to take Fn, and I want to form its Z transform, F of Z, which by definition is equal to the sum over all values of n of Fn, which is A alpha to the n, times Z to the n. And let's for a moment assume that the absolute value of Z is less than 1, and that alpha is less than 1. So I can sum this series. Now, does anybody remember how to sum a geometric series? You learned this in junior high school. Yes, say it out loud, please. Okay, he said it's the initial term divided by 1 minus the common term, alpha z. Not quite. For this sum, you're correct. But in fact, suppose I'm going to do this in red now, because you need to know this. If I take this from n equals n1, not 0, up to some number n2 of, say, a alpha to the n, now can you correct what you said? This is something you need to know. You have to know how to sum a geometric series. And it's very simple. I'll tell you what it is. Basically what he said. Okay? What it is. It's the first term minus the first missing term. Over 1 minus the common term. So let's write that out for this. What's the first term in this series? Anybody? Not A. A alpha to the n1. What's the first missing term? Well, you guys are mumbling a little bit, but the first term that's not there is not n2, it's a term after n2. So it's A alpha to the n2 plus 1. What's the common term? Common term is alpha. That goes with, okay? Now, I want you to memorize that. And it's easy to think of the words. It's the first term minus the first missing term of 1 minus the common term, the common factor. I've taken the A out of this, if you will. Okay? That's important. We're going to come across that over and over again. So, for what I have in black here, then, what is the answer? What is the sum of A alpha to the n from 0 to infinity? First term is with a 0, says plain old A times 1. There are no missing terms, so put the A up on top. Oops, and the common term, sorry, it's A up on top over 1 minus alpha. That's the easy one, okay? Well, this is the first Z transform pair we found. It's a very important one. So I want to circle it. That's the most common one we're going to need, by the way. This is not an accident. This example is an important example, as I said. Now, there are many pairs that people have worked out. You can work out some of them. And I'm going to show you a table. It's table I2 in Appendix 1. Let's see, where is it now? Here it is. This table is in the book. And the one we just found was number 6. We just identified this one. But there's lots of them. Some of them we're going to derive, but you can go to tables of Laplace transforms to help you go from time to transform domain and backwards. If you see, for example, this, you know immediately what time function it came from, A alpha to the n. And it turns out we're going to be using this particular one to help us get out from the Z transform always. Okay. So let's go back. Okay. Now, while we're at it, I'm asking you to memorize the red thing. You should have known that coming into this class. I'll ask the question the easy way. How many of you have never seen this red expression? Don't be afraid. How many of you have seen it? You don't want to answer, do you? Okay. Okay. You've seen it somewhere in education. But anyway, it's true. Check it out. Okay. Now, here's a useful trick. I'm going to write this in red, in fact. Which is related to what we're talking about here. We know that the summation of alpha to the n from 0 to infinity is 1 over 1 minus alpha. The question is, how about the following? The sum from 0 to infinity of n plus 1 times alpha to the n. I doubt any of you have that in your head. But you have the tools to figure it out. Because we know that the I'll use it as a partial derivative, you could use a total partial with respect to alpha of alpha to the n plus 1. That's reminding me we've run out of the first hour. Let me just finish this. The partial of alpha to the n plus 1 is what? N plus 1 alpha to the n. And we can use that. Let me just finish this then. So the summation of n plus 1 alpha to the n from 0 to infinity is equal to the partial with respect to alpha of the summation of alpha to the n plus 1. And what is that sum on the right? It's the partial to alpha of what? Can anybody do the sum? I just told you how to do it. What's the first term? Alpha over, and no missing terms, over 1 minus a common multiple. Now, if you differentiate that, you got the answer. Okay? Well, remember how to differentiate? A ratio, denominator squared, denominator times the difference. Numerator, okay? It's 1 minus alpha squared over 1 minus alpha, the numerator, the denominator derivative of the numerator is 1 minus the numerator derivative of the denominator, which is minus 1. So the whole answer is 1 over 1 minus alpha squared. Easy. You're going to see this. The homework that's due a week from Wednesday. And you can do this multiple times. If you had n squared times alpha to the n, you got to do it twice and monkey around with it a little bit. Okay? So I want you to remember this trick. It's a very useful trick, using differentiation. It's commonly used. Okay, good time for a break. Let's take the break. Rohit, you want to address this young group?
Hey guys, I'm a grad student with Professor Kleinrock. I have the book on
Doesn't make a difference, but for the recording, I guess it does. Okay. Thank you. So convolution, which is a complicated operation in time, becomes a very simple operation in the transform domain. And that suggests if we can move from time into the transform domain, manipulate, and come back out, we have another path to doing this complexity in the time domain. And we're going to use that over and over again, as you'll see. And let's look this table. This is in table I3. Let's look that one up, just to show what it looks like. This is entry 10. It's the one I just noted here. Oops. It's this one right here. But there's many properties, as you see. And you should take advantage of these as well in solving problems and doing some homeworks. Okay. And by the way, I believe these tables are copied in the Brew and Learn, but they're in the book, so you can see them there directly. Okay. Okay, now we'll define something else. I want to define something called the unit function. And it's also known as a Kronecker delta function, if those of you have heard of it. It's defined as follows. It's u sub n, and it's equal to the value 1 for n equals 0, and 0 anywhere else. Very simple function. And it turns out that if you feed u sub n into a discrete system, out comes a sequence h sub n, which is called the unit response to the unit function, the unit response. And it turns out that happens to be one way to determine those h's we talked about before for discrete functions. We're not going to go into it too deeply right now. But for more properties, let's look at table I1. And here's properties of the Z transform. It's in table I1 of your book as well. The thing on top is, of course, the definition of the Z transform. Here's the definition of linearity, etc. Very useful properties that are all about the theory of transforms. Now the question is, how do we go back from Z to N? From the Z transform to the N domain. Namely, if I have f sub n, double arrow f of z, I just showed you how to go in this direction. But how do you go back? If we're going to work in the Z transform, we have to be able to get out of it. Well, the most significant way to do it is something called partial fraction expansions. And basically, it takes a rational function of z and converts it to sums of equal functions whose inverse we know. So let's assume that f of z, the thing we're trying to invert, is a rational function, namely a polynomial over a polynomial, a numerator polynomial n of z over a denominator polynomial d of z. And let's assume that the degree of numerator n of z is less than, strictly less than, the degree of the denominator. And if that's not the case, we can divide the numerator by the denominator until the remainder has this property. And the things that pop out from that division we'll handle separately, as you'll see from the table I just showed you. Okay. In fact, let's look at table I8 again. Entry 8 of table I1. Let's look at that one just a second again. If you look at entry 8 here, this one right here, I'm sorry, this one here. See that z to the k times the function? When you divide the numerator by the denominator, you're going to pull out powers of z until the numerator degree is less than the denominator degree. And if you get z times something, its inverse is just a time-shifted version of the function itself. So that's how we're going to get rid of the degree problem. And you'll see that in some of the examples. Okay. Okay. So now let's try to write this out in general, because it's not yet clear how to do that. Let's assume something. Let's assume that the denominator is already factored. It's a polynomial. Let's factor it. In big red letters, this is the only hard part, to factor it. You may have seen this issue in your earlier mathematics studies. Factoring polynomials is the only really difficult step in many of the transactions and operations you have to go through. Factoring polynomials. Now, we're not talking about cryptography and factoring primes, just finding roots of a polynomial. That's the only hard part. So let's assume it's been done for us, and I'll show you how to do it in a minute. So let's assume that d of z is already a product of factors. Say its product, say, I equals 1 to k of 1 minus alpha sub I z, that's a factor. But let's assume this has multiplicity m sub I. So the ith root is 1 over alpha I of multiplicity m sub I. You may have multiple roots. Okay? Now, if that's the case, and that's the hard part, as I said, then you can write f of z, d of z as follows. Or f of z, I'm sorry. Then f of z is the following. It's a bunch of terms. First one is going to be called a11 in the numerator over one of those roots, 1 minus alpha 1 z to its multiplicity m1 plus an a12, same root of 1 degree less multiplicity, 1 minus alpha 1 z to the m1 minus 1 plus dot 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 all the way down to plus a1 m sub 1 of 1 minus alpha z, 1 minus alpha 1z. That's for the first root, okay? But there's k of them. Now similarly for every other term, plus dot 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 plus finally down to a sub k1. There are k roots, so the first term is going to be k1 over 1 minus alpha k times z to the multiplicity m sub k. And you know the rest. It's going to be a sub k2 over the same root, 1 minus alpha k z, to one less multiplicity, mk minus 1, plus dot dot dot, plus finally a sub k, the m sub k ak, of 1 minus alpha kz. So a whole bunch of terms. Now if the multiplicity of each of them is 1, you just get a bunch of these last terms. It's an a1 over 1 minus alpha 1z plus an a2 over 1 minus alpha 2z, etc. Okay. Now let's look at those terms again. Let's go back to table I2. And look at entry 13. Right here. There is a pole of degree m plus 1. Here is its time domain. So we can use this item 13 to undo each of these guys, but I also have to tell you what the a's are. So let's go back to our picture now. Aij, oops, is the following. It's a little complicated. 1 over j minus 1 factorial times the root to the j minus 1 power with a minus sign, 1 over alpha sub I to the j minus 1. Whoops, what's all this? Times the differential. The j minus 1 differential of the following. Of the numerator over the denominator times the factor this is related to, namely 1 minus alpha I z to the m sub I. Close that bracket. But we have to evaluate the whole thing when z equals the root 1 over alpha I. So let me move this over. I'm going to cheat on you by moving this over. You can't do that, but I can. And I'm going to evaluate all of that at z equals 1 over alpha I. So this looks a little complicated. It is. When you have multiple roots, it's a pain in the neck. But it's all prescriptive. Okay? We're going to do an example in a moment. And the simple version of this, if the multiplicity is 1, then you know what it is. It's 1 over 1 minus alpha I z. Namely, a alpha I to the n. So let me do an example. Finally. Sorry about that. Kill this for me, would you? Thank you. Let's do an example. It's not too easy, is it? Okay. Let's take a function, f of z, that I want to invert. Let's assume it looks like this. It's a rather simple example. In the numerator, it's 56 minus 18z over z squared minus 6z plus 8. That's a z transform. Let's invert it. Okay? Well, anybody know what the roots of the denominator are, the hard part? Excuse me? Yes, 4 and 2. The hard part you did for me. Thank you. Okay. So let's write that out. That's equal to the same thing, 56 minus 18z over 2 minus z and 4 minus z. Now I'm going to divide everything by basically 2 times 4, 8, and I'll get the following. I'll get 7 minus 9/4 z over 1 minus a half z over 1 minus a quarter z. Now it looks like the form I saw. It's already in that form we saw earlier. And notice they're all simple roots. So let's actually go through the ugliness of making this happen. Let's recognize that that's a sum of 2 factors. One of them is 1 minus a half z. And what do I do in the numerator to get that term, that a term which you talked about up here? This black term on top of the screen. You multiply by the root you're after. So let's do that. It's 1 minus a half z times the function we started with at z equals the root, which is z equals 2. And we'll work that out in a minute. Plus the other part, downstairs is 1 minus a quarter z. And upstairs we're going to multiply by the root after 1 minus a quarter z times f of z, evaluated where? At the root, z equals 4. Okay, let's actually do that. I'll get 7 minus 9 halves over 1 minus a half. That's that numerator I just did. All of that divided by 1 minus a half z. Plus, next term, 7 minus 9 over 1 minus 4 over 2. All of that of the 1 minus a quarter z. Okay. And that gives me simply 5 over 1 minus a half z plus 2 over 1 minus a quarter z. Now, do you recognize those terms? Each one of those was the form of an a alpha to the n transformed. It's a over 1 minus alpha z. So f sub n, which is the inverse of that, is simply 5 times alpha to the n, which is a half to the n. Plus the other one is 2 times a quarter to the n. And that's n equals 0, 1, 2, etc. Done. Okay, that was a baby example. You have some for homework, believe it or not. And some of them are a little more difficult. And if you get some multiple roots, you got to play the game up here. And if you don't have a degree of numerator less than the degree of denominator, you got to divide out and use that term I showed you. Okay. This is not hard. This is a nuisance. The hard part is what you said, namely, what were the roots? This step right here. In general, that requires some computation of some sort. Okay. End of that topic. What's left? Continuous time. Transform is called Laplace transform. Let's go for it. Okay? So let's go to Laplace transform now. Now, I'm making you suffer with all of this is just a tool that I'm showing you how to deal with discrete functions. And in a moment, I'm going to show you where they might arise in queuing systems. But this technique of finding roots and inverting is key. So in this case, we're going to take a function of continuous time f of t and write its transform and call that f star of s. Star, in this case, means transform now. And what is it? Well, f star of s, this Laplace transform, is defined to be the integral from minus infinity to infinity of the function f of t e to the minus st dt. Once again, this e to the minus st is just a tag. So I can find the elements of f at various points in time. Think of it that way, but functionally and operationally, it's very useful. And by the way, this minus infinity is there if it's a two-sided function. If f is one-sided, namely f of t equals 0 for t less than 0, then that becomes a 0. And that's the one we're typically going to use because the f's we're going to deal with will be a function which can only be positive. Okay. Now, just to note, z equals 1, which we haven't focused on, is like basically s equals 0. Because remember, z was an e to the st function. And we're going to have values. It's going to be valuable for us. Okay. Now, let me go through an important example in continuous time. This is very much like what we did for discrete time. An important example is going to be f of t equals a e to the minus t, e to the minus at, for t greater than or equal to 0, and 0 for t less than 0. It's a strictly positive function. Why am I choosing it to be positive? Because this function will represent a probability for functions which can only be positive for positive time. The time between arrivals can't be negative. The service time can't be negative. So I'm anticipating that ahead of time. Okay. So what's f star of s here? It's the integral from 0 to infinity of a e to the minus at, the function I'm trying to convert, times the transform variable, which e to the minus st dt, and that's clearly equal to a integral e to the minus s plus a t dt, which we all know is capital A over s plus a. That's a very important pair. It's a very common pair. It's similar to the a over 1 minus alpha z. Okay. Let's talk about convolution in this case, as we did before. We want to convolve f of t and g of t. Now, this is very similar to what we just did. It's defined as follows. F of t convolved with g of t is by definition the integral from 0 to t, assuming the f and the g are both only over the positive time axis, f of t minus x, g of x dx. And the Laplace transform of that the Laplace transform of the convolution of two functions is basically, and you can see very easily see that, that's the product of the transforms of each, just like in discrete time. And that's in the table that we saw before. Okay. Now, how do you invert from the S domain, Laplace transform domain, back to the time domain? Very similar to what we did before. To invert, we're going to use partial fraction expansion again. So we're going to assume that the function we're after, f star of s, is basically a ratio of two polynomial. It's a rational function, n of s over d of s, where, of course, the degree, once again, with the degree of n of s is strictly less than the degree of the denominator. Now we're going to factor the denominator. Again, in red, this is the hard part. Once we do that, we can write d of s as a product of a bunch of factors, I equals 1 to k, just like before, of the factors s plus a sub I to the multiplicity m sub I. And if that's the case, then f star of s can be written as the sum of these terms. And let's write that out like before. Instead of the a's, I'm going to use b's for the coefficient now. It's b11 over the first root, s plus a1 to the m1, its multiplicity, plus dot, 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 plus b1 sub m1, its multiplicity, over s plus a1 to the first power, plus dot, 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 plus finally b sub k1 over s plus ak to its multiplicity, plus dot, 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 plus b sub k, m sub k, there's mk of them, over s plus ak to the first power. And of course, the important pair is the one I mentioned before. It's this one up at the top of the page. And that came from an a e to the minus at. We're going to make use of that. But what are the b's? Just like before, those coefficients are sort of tricky. B sub ij is equal to 1 over j minus 1 factorial. And all this is in the books. You don't have to copy too carefully. Times the j minus 1 derivative with respect to s of multiply by the root you're trying to find. So multiply by s plus ai to its multiplicity m sub I. And what's left is the function f of s you're trying to invert, that namely the numerator over denominator, evaluated at the root. S equals minus ai. Let's do an example, a simple example. Let's assume that f star of s, the thing you want to invert, is simply 3s plus 1 divided by s plus 3 times s plus 1. I've already factored the very difficult one for you here. Notice I also chose one where the degree of the numerator is less than the degree of the denominator. And if not, you divide one by the other, get terms, powers of s, and use that transform term. Use the one in the table. So this is equal to, by definition now, it's b11 over s plus 3, that's the first one, plus b21 over s plus 1. And b11 is like before, multiply by the root that you want to get rid of, s plus 3, and take the rest of it, f star of s, and evaluate it at the root s equals minus 3. And what's that equal to? When you look at the function, it's 3s plus 1 over s plus 1, evaluated at s equals minus 3, and that turns out to be 4. And b21, same kind of thing, it's s plus 1, the root you want to get rid of, times what's left over, f star of s, at that root, s equals minus 1, and that's equal to 3s plus 1 over s plus 3 at s equals minus 1, and that turns out to be minus 1. So what do I have? Clearly, f of s is very easy now. We can write it out. F star of s is equal to 4 over s plus 3 minus 1 over s plus 1. And how do we invert that? What does 4 over s plus 3 give me? The one famous pair, the one up here, right there. It's going to be the numerator over e to the minus root times time. Okay? So simply 4 times e to the minus 3t minus 1 times e to the minus 1t. Done. And if you wanted to check this, what would you do? If you wanted to check that that answer is correct, what would you do? Namely, that you correctly transformed this thing, inverted it. What would you do? Quiz problem right now. What do you do? I'll give you 1 minute to finish it. I've lost you all. Yes? Form the Laplace transform of this thing on the bottom of the page. And you'll actually work back through these steps to get that. And if you get that, you did it right. If you didn't, you made a little mistake. Try it again. Okay? Good. Now, all this has been a set of tools. Now let's use it. Let's write down to discuss use of transforms. We just studied transforms now. To solve difference and differential equations. That's why we did all this. We're going to confront difference equations and differential equations in our study of queuing systems. We want to solve them. And typically they're hard. If you go into the transform domain, it's easy. That's the whole point of this lecture today. Okay? So let's start with difference equations. I'm going to do it by example. It's probably easiest to understand that way. I want you to find an explicit expression for Fn where Fn is given to you as a difference equation for its own values. So let's assume we're given that 6 times the function I'm looking for, 6 times Fn, minus 5 times Fn minus 1, plus fn minus 2 is equal to, say, 6 times 1/5 to the n. And this is for n equals 2, 3, 4, etc. Now, these kinds of equations will arise when we study queuing systems. But you've seen difference equations before. Have I completely specified this equation? Is there something else I have to say in order to try to attempt this? It's a second-order difference equation. Yes, exactly. So I'm going to give them to you, okay? We need two initial conditions. Let's assume that f0 is itself 0, and f1 is 6/5. Ready to go. Now, one thing you could do, you could laboriously solve this iteratively. Start with n equals 2. 6f2 is 5 times f1. f1 is 6/5, plus fn minus 2, which is 0. Gives me f2. Once more, f3, blah, blah, blah. You keep going forever, because I want you to give me fn for any n. Okay? Okay? So we're going to use the method of z transforms. Now, what I'm about to write down, I want you to pay very close attention to, because we're going to use this over and over again. Taking, in this case, a difference equation, and how do we solve for it? So, step 1. Multiply the nth equation by z to the n, and sum over the range for which it applies. So let's write that out. I want you to stamp this in your head. You have to understand how to do this, okay? Multiply the nth equation by z to the n, and sum over the range. So let's do that. Let's do that for this example. That's step 1. So let's see. I'm going to take this nth equation and multiply everything in there by z to the n. So let's do that. 6 fn z to the n plus, minus 5 fn minus 1 times what? Come on. Z to the n, not z to the n minus 1. Z to the n. It's a multiplying equation by z to the n. Okay. That's an easy mistake to make. Okay. Plus fn minus 2 times z to the n. But now I got to sum it all. So put a sum in front of everything. And what range do I sum? 2 to infinity, right. Now I've got to stick a little sum in here, sorry. N equals 2 to infinity, and the sum here, n equals 2 to infinity. And all of that on the right-hand side, I have to do the same thing, right? Sum n equals 2 to infinity of 6 times 1/5 to the n. And I'm out of space. I'm going to cheat again. I'm going to move the equation over. Oops. This is pretty ugly here. 1/5 to the n, z to the n. Okay. So I did what the first step told me to. Okay, let's consider step 2. Step 2. Match the power of z with the f subscript. Okay, let's do that. So I look at this first term, fn z to the n, they're already matched. Okay, let me take the 6 outside just for fun. That gives me 6 summation n equals 2 to infinity of fn z to the n. Nothing to do there. Minus, let's take the 5 outside. Now let's see. The z to the n doesn't match fn minus 1. So let's pull one factor of z out and be left with z to the n minus 1. So I'll 5z, okay, times the sum, n equals 2 to infinity, of fn minus 1, z to the n minus 1. Next term, it's off by 2 factors of z, so let's fix that. Let's take out z squared, and take the summation from n equals 2 to infinity of fn minus 2 z to the n minus 2, and all of that equals, and I may as well sum this guy already, because that's a standard geometric series. So I'm going to ask somebody again to sum that for me. Okay? What is this right-hand term? The summation of 6 fifth to the n z to the n. What's the rule? First term minus first missing term of 1 minus a common term. What's the first term in this sum right here? It's 6 over 25, a fifth squared, z squared, right? No missing terms, all of that of 1 minus z over 5. Oops, let me write that clearly now. Yes? Okay. Now, once I've done that, I should be able to recognize f of z. So I'm going to call that another step. I don't usually identify that step. I say, okay. Note f of z. Let's do that. So in this first sum, I've got 6. And how am I doing with this first sum? Let me... this sum is what? It's almost f of z, but it's missing the terms 0 and 1. So let's write that down. Let's write down what I have there is f of z, but I have to take away 2 terms I didn't have, which is basically the 0 term, which is f0 z to the 0, minus f1 z to the 1. Now, I want you to get used to doing this because you're going to be doing it a lot. Minus 5z, and that sum, again, is missing how many terms? When n is 2, it's f1 z to the 1. So I'm missing the 0th term. So let's write that down. That's f of z minus f0. The third thing is z squared. And how's that guy doing? That's all f of z, right? When n is 2, I start with f0. Perfect. So that's f of z. And on the right, I've got the thing I did before. It's 6 over 25 z squared over 1 minus z over 5. Okay. Now, the next step, solve for f of z. Okay, let's do that. I've got f of z is equal to a bunch of stuff. It's equal to 6 minus 5z plus z squared. And on the right-hand side, I got all the rest of the stuff, which is 6f0 plus 6f1z plus 5 plus 5f0 times z. And then this other term that I stuck with here, it's 6/25 z squared over 1 minus z over 5. But, as you told me, there were initial conditions. So let's note that but f0, here's where you plug in the initial conditions. f0 is 0, and f1 was what? f1 was 6/5. So plug that in. So let's call that step number 5, just for the fun of it. 5, initial conditions. Thank you. Okay, we'll just finish this up now. So now solve this thing for f of z. Let's do it in black. And it's equal to 36 over 5z times, and I'm doing a little factoring already, 1 minus z over 5 plus 6/25 z squared over 6 minus 5z plus z squared, that factor from the right, times what I had from the left, 1 minus z over 5. And it's not complicated. I can ask you to do it again. Factor that lowest term in the denominator. This thing is simply equal to 3 minus z. That's the hard part ordinarily. 2 minus z. And now we can multiply by appropriate constants. Time is running out. The period's over. So I'm going to go dot, 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 and let you play with this. You just do a little bit of arithmetic. That's going to equal minus 9 over 1 minus z over 3, if you do the partial fraction expansion, plus 8 over 1 minus z over 2, plus 1 over 1 minus z over 5. Last step now, invert. To get Fn. And we can see immediately what that inversion gives me from the equation at the top of this page. It's going to give me that f sub n is equal to minus 9 times a third to the n plus 8 times a half to the n. This is obvious by inspection. Plus 1 times a fifth to the n. And this is for n equals 0, 1, 2, etc. And now, for any number value n, 152, I can tell you what Fn is. Just plug it in. So that was a rather straightforward. I did some very simple things in the z transform domain. The only hard part was factoring. But instead of doing what we started to do before, was iteratively solve for this thing or some other mechanism you have. I mean, you can try to find the homogeneous and the particular solution, which is what you learned in school for difference and differential equations. What's wrong with that procedure? What's nasty about it? Solving it in the time domain with the homogeneous and the particular solution. What's hard about that? Anybody remember? What did you suffer with in high school? You liked it? Yes. You have to have a good guess. Exactly right. You had to guess the particular solution. Well, what the hell is it? Maybe I'm a good guesser, maybe not. No guessing here. Just solve for roots. So there are simpler things in the transform domain than in the time domain. So we like to drop into the transform domain as soon as we can. But notice what's going on in this process. We have something in time to solve. The equation we got probably came out of good reasoning. I wrote down that difference equation from the physics of the problem, or the differential equation. A car moves along a river, blah, blah, blah. You understand what's going on, so you write down this difference or differential equation. Then you got to guess. You don't want to guess. You go into transform domain. Once you go into the transform domain, your mind is blown. You can't think about the physics of the problem anymore. It's gone. You got z's, you got roots, you got coefficients. You know, where's the guy sliding down the river? He's gone. So you gave up good engineering reasoning and argumentation for simple mathematics. And often it works very well. At the very end of the course, I'm going to tell you there are ways to stay a little longer in the engineering domain without giving up too much. So you can use your engineering reasoning, your science reasoning, instead of just your mathematics mistakes. Okay? So, okay, very good. We'll do differential equations next time. See you on Wednesday.